Hello, Rob. Today we're going to be talking about the constant speed of light and its consequences. So the speed of light in a vacuum is constant for every observer, regardless of their motion. Now, this single fact, it breaks our intuitive understanding of time and space entirely. In everyday life, speeds add together. For example, if you throw a ball forward on a moving train, the ball's speed relative to the ground is the train's speed plus the throw. This is what you would think would happen if we were on a train and the train was moving this way and there was someone standing here and they saw you throw a ball in this direction as the train was moving in this direction. And they would see the speed of the ball move faster than you would see. The person standing on the ground would see the ball move faster than the person on the train. This is called Galilean relativity, and it works perfectly at relatively low speeds. However, light does not behave in this way. Whether you are stationary or moving toward a light source at high speed, you will always measure light traveling at the same value. So light always has a value of 3 times 10 to the 8 meters per second, no matter where you are standing on or off the train. So C is always 3 times 10 to the 8 meters per second. And that is constant for all observers. Now, for this to be true, something else must change. That something is time and space itself. So let's talk about time dilation. We've talked about this a little bit in another video. But if the speed of light is fixed, that means that if the speed of light is fixed, then time must run at different rates for observers moving relative to each other. So a clock on a moving spacecraft, it actually runs slower than an identical clock on Earth. Now, this is because of time dilation. So the thing to remember here is moving clocks run slower. For example, if we have a person standing on the surface of the Earth, and then there is a person in a spaceship, and then this spaceship is at about 0.98 the speed of light. Now, if we had a clock on both these observers had a clock, then the clock on the spacecraft that's traveling near the speed of light will experience time slower. So the clock will be moving slower on the spacecraft. In the person standing in their frame of reference, their clock on the spacecraft will be moving slower compared to the one on Earth. Okay, so moving clocks run slower or run slowly. Now, there's also another thing that can happen, and that's called length contraction. So the constant speed of light also requires that distances contract in the direction of motion. So if we look at the same example, if we have a person standing on the surface of the Earth, and then we have a person in a spaceship. And let's say the spaceship is again at 0.98 the speed of light. Now, if the person on Earth was able to measure the spaceship, let's say they were trying to measure the length of the spaceship. Now, what they would see is that the spaceship would actually shrink or contract in the direction of motion. So they might see the spacecraft to be this big, but in reality, when the spacecraft is not moving at the speed of light, its length is actually longer. It might be more like that. So it really depends on the speed of the spacecraft and where the observer is positioned. An observer on the spacecraft, they will measure the spacecraft to be exactly the same as the person when it's at rest, because they are in the same frame of reference. But for an outside observer who is standing stationary on the Earth, they will see that the spacecraft is actually shrinking in the direction of motion. That's a geometric consequence of how space and time behave at relativistic speeds. So to summarize that one, we have moving object appears shorter in direction of motion. Shorter in the direction of motion. Okay, so to summarize, because the speed of light is constant for all observers, time and space cannot be absolute. Time dilation means moving clocks run slower relative to a stationary observer. Length contraction means moving objects are measured as shorter in the direction of motion. Both effects are negligible at everyday speeds, but they become significant as velocity approaches c. Now, in the next video, we'll go over this a little bit more, but that is an introduction to length contraction and time dilation due to the constancy of the speed of light.